There it is.
It is. Hey, everybody. Good morning on the live recording here, the 7th of March of our 54th program. I am Baron Ron Herron, and as we slowly phase back into a post-COVID lifestyle again with our second online general meeting through Zoom this past Friday, March 4th, we are Santa Barbara's Astronomical Unit, the South Coast Longtime Telescope and Astronomy Club. And this is the SBAU Astro Hour, done live from our man caves and computer rooms. There's 6 of us on screen this morning, and you can watch on YouTube and see all the past programs. We've done 52 a whole year, and now we're into our second program of the new year, the second year. It is the 7th through the 13th of March. This week, we're going to talk about the moon's Vertex mission coming up in 2 years. What exactly are solar swirls? Scientists don't know. That's our moon. We look at another nebula, M57. M57 is the ringed one. And what exactly happens inside the sun? This should be our Astronomical Unit newsletter sent out by one of the people I'll introduce you to here in a minute. Actually sent out by one that you're not going to see, our treasurer, but edited by our ex-Westmont College guy. Let's meet the president, Jerry Wilson, wife Pat. Good morning, sir.
Good morning.
You want to introduce your dog? Is it going to make an appearance? You suppose it's down below you, right?
Yeah, I don't want. She's finally calm and laid down. I don't want to disturb her. Let sleeping dogs lie.
That was the most energetic dog I've ever seen at one of those parties we had up at Cachuma Lake. Here is Chuck McPartland, outreach coordinator, married to another Pat, who was our merchandise manager. Chuck's got a problem, or actually not a problem, but a cat thing. Actually, they embellish the program when it blocks your face, Chuck. Sorry about that. We'll check with you on outreach, what we're doing. Tom Totten is our incredible webmaster, gets us on and off every week. And amazingly, I don't know how you swim through these waters of technicality, but a wizard and former president, Tom, thank you. And give our love to Cezanne, your artiste wife. Tom Whittemore is on board, former Westmont College science instructor. Tom.
Yeah, morning.
Baking a lot of sourdough bread these days. He also, as I said, edits our newsletter. And you do a darn good job. Married to Maureen. Bruce Murdoch is a longtime active member, also the president of the Santa Barbara Theater Organ Society. Bruce is married to Bonnie. Tim Crawford, not on screen, but he is a staunch supporter and the man that used to run the Tuesday night programs, which are still on Tuesday. Tomorrow night, 7:30 to 9, we do a telescope.
Jim Williams is watching, Ron.
Oh, is he? You can tell?
Yep.
You've got the pulse of YouTube.
He's on the YouTube chat.
Well, real quickly, Friday night, who else was watching besides the SBAU or the SBCC? Actually, he's an SBAU member. Sean Kelly, wasn't he on board?
Yeah, you're right. And Chrissy Cook was in chatting, and Tim, and
one other guy
others
that we know of.
And we really should include
Chrissy.
We should include Chrissy as one of the participants rather than just a visitor in those things.
Does she have a new title, or is she reclaiming a title she did have with the Museum of Natural History, where we used to be?
She used to be there. She was pre-Javier.
Oh, so she's taken over Javier, our connections to the museum's place? Is that true?
Yes. He took it over from her, and now she's taken it back over from him. She's come up through the whole museum program from when she was a teenager in the quasars.
Quasar? Is that the name of a club?
It's the Quasars to Sea Stars. It's one of their programs for junior high, and I think maybe starting high school students to do sort of community credit, to do community service.
The rest of you
and learn about it and learn about things.
Any of the rest of you heard of quasars before? I hadn't.
Quasars to Sea Stars.
Okay, and there's also a little Girl Scout club, or at least a kids astronomy.
No, it's a Girl Scout club, and they're observatories in Ojai.
Well, Totten, your assignment is to get some cookies from them.
Oh, great.
I guess before we go to the
Chrissy also is a representative that has Girl Scout cookies available for sale.
Yeah, right. Damn it, that's what put a lot of my weight on. But I love those little thin mints and s'mores. Give me some more s'mores. We'll probably be live together in about 2 weeks at Westmont. No, actually 1 week at the museum. Mr. Outreach, would you like to tell us about that?
Yeah, we're going to restart our public monthly observations, second Saturday of every month at the Museum of Natural History. So we set up along the roadway there that goes to the observatory from the parking lot, starting at 7 o'clock. And we're going to, at least for March, we're going to ask everybody to wear masks because they're going to be in close proximity by the telescopes.
Yeah.
And then we're going to restart our third Friday of every month. So on the 18th, Friday the 18th, we will have our Westmont Public Telescope Night at their observatory, which is next to their athletic fields. And that also starts at 7, and that also will have masks required. There's the Westmont page.
Are all you guys going to be there? Whittemore, I'm sure you will.
Yeah.
Old alma mater. Yeah. Bruce, you going to be able to join us?
No, I'm not going.
Okay. Before that Darkness Falls thing we do next Saturday, we'll have a board meeting that could folks drop in on that? Aren't we going to be just sitting around outside the observatory at the museum?
Well, that's for club members, yeah.
Yeah, club members only. Well, that's when we could get the cookies, doggone right.
Hey,
Can we
Chuck,
go to some?
Chuck, any chance that we're going to open up the outreaches out at the what do you call it? The Ritz-Carlton?
I have
Where?
talked with a person there. It's new people, you know.
Okay.
Since the pandemic, I've emailed the people there and I've told them we were restarting our public observations.
Okay.
They have so far not requested us to come back and do our repeats of every Thursday during the summer, but that's usually June.
Okay.
They have asked us to do a couple of corporate events, but both of those happened to be when Omicron started to surge, and we told them, no, sorry, we can't.
Yeah, it's always been a favorite of mine.
Yeah.
You know.
Now, the Miramar is going to have us back, so I'll let you know about that.
Yeah, that I love that one too. Nice, cozy observing area.
Yeah, yeah. Unfortunately, a bit of a lug for the equipment, but
not mine.
yeah, not yours.
My little refractor.
All the members of SBAU get notices from Chuck, and we get the newsletter, so we'll know. And we still have over 200 members, do we not, Mr. President? You think?
I don't know. That was Colin keeps the roster. It was frozen 2 years ago, and so it's the same roster. We haven't updated.
I think it's closer to 150.
Yeah.
Okay.
Yeah, I wonder what happened 2 years ago. I was out of town. Something happened. Okay. Can we go to the
I've
silly
never
stuff?
been at the Miramar for an outreach. Where do you park? And where do you end up?
This is a limited group of people because they have a really small little lawn that we set up on.
Okay.
And it's quite a lug. I don't think you'd be able to get that 11-inch in there.
I can put it on a cart.
Yeah.
Well, even so.
Okay, let's get to this today's.
Let's get to the silly science stuff first, and then into the heavy stuff about the moon and a M45 or 75, whatever. I want to just quickly say Riley Lynn Lewis did a great talk. Boy, it was well documented and displayed about the exoplanets Friday night. I still got a call into LCO, that's Las Cumbres Observatories based in Goleta, with a director who's going to try to find us a speaker for next month. If I don't hear back from anybody this week, I'll go after somebody else, and we should be able to get a speaker on the 1st of April. That'll be our next live general meeting, our big third.
No fooling.
Ron, the person in contact there, I think, is Sandy Seal. Not the director, but Sandy Seal, who is like their community liaison person.
Well, what Tom Totten sent to me had a whole bunch of email connections, and I just went to the director, Dr. Lisa Laurie, or
yeah,
she
might be at too high a level for that.
Yeah, and she said she put the word out. So
okay,
maybe the lady you talked about doesn't feel slighted. So we'll see what happens next month. Are you ready, Tom? Call up anything,
Sure.
and I'll see if I can match it here. These are silly science things. And some of them are very, very, there you go. Energy, EMC squared. What is energy and mass? It's milk and coffee squared, by golly. I love that one. Is that the classic one? Oh no, the classic is converting. Oh, here's the contest on the moon between two astronauts. One of them definitely has to tinkle, and boy, does he tinkle. So there is water on the moon.
If it were only that easy, right?
Yeah, but you know, when he unzipped, it was kind of sad. He lost all his air.
Yeah.
Go to another one. These are great. Coming from, a selfie. And it's not a telescope, but it's a real life living cell checking itself out with a microscope. I assume that's what a CELL selfie. All right. Oh, I like this one. Really getting lost. Couple aliens land their UAP. What does the U stand for? Is it unexplained aerial phenomena? Unauthorized? It's something a spacecraft at Andy's Gas and Go for a fill up. That's what flying saucers apparently use, our fuel. And he says, hey, you guys not only got the wrong planet, you got the wrong solar system. I mean, a wrong planet I can understand, but a whole damn solar system? You might also have said, you know, we got out of control inflation here. Your gas is about $8 a gallon, gentlemen. Okay. That's where I get my gas. It used to be terrible herbs. Okay, this is a good one. Everybody like this. See if I could, renaming and rebooting the constellations like Slingshot,
this.
Camel, Wind Chime, and there's one called I've Fallen, but I Can't Get Up, or Need Help. I guess that's at the bottom.
Of course, also Phil.
They cross out the others. That all? That's all 12 of them, isn't it? Or 12 in the zodiac. Or are those the zodiac constellations? Yeah, they are.
Yeah, there's 12 of them there.
We didn't get any Pegasuses or Cassiopeias. All right, here's the oldest trick in the book. Black ink on the lens of the big telescope. If you look carefully, a couple of snickering astronomers, old guys in the foreground, pointing to the poor old geezer stargazing scientist behind him, just had his eyes blackened. Okay. Silliness abounds. All right. Oh, converting feet into meters. There's your meter. Now give me the foot. Good Lord.
Yeah.
Something we definitely need to do. Okay. Forwarded silly science cartoons. Somehow we got to figure out a way to get those to the people that are members if they wanted them. But Jerry, what do you want to talk about? Shall we go out to the moon first quarter?
Whatever you like.
I'd like to take it a step. But actually, is there anything you could say real fast about James Webb?
No?
Nothing. I heard it was done. It's ready.
No, I haven't heard that.
Well, I get a lot of stupid videos on YouTube that.
You got to be careful. There's a lot of.
They say, look, we discovered this new thing, blah, 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 blah. Wait a minute. They're not to that point yet.
Yeah.
Well, yeah, they have all kinds of new pictures, and I just got to be from Russia. However, our favorite satellite is up there with not direct sunlight on it. It's nowhere near full, but it's a quarter, half full, the taco size, not too bright.
Oh, you mean the moon?
Yeah, we're out at the moon.
Yeah, the moon will be first quarter this week, probably tomorrow or the next day.
Okay.
This one is a really nice image of the moon, taken in dusk. See how bluish the sky is. It's not dark. It gives a good lighting.
What, Bruce?
Is this Jerry's photograph?
No, I didn't take I took this off the web. I didn't take the picture myself.
And it's got the lunar X.
Yeah.
Where?
Right there.
Right there.
That's the X?
There's the L. Yeah, there's the L, there's the X, and the V is up top.
It needs a Y-axis, X-axis, Y, big cross on the moon. And the shadows are different. The sun's not directly on it, so we see different things.
Yeah, it heightens the contrast along the terminator. It's a really good time. You can actually, if you view over several hours in an evening, you can see the shadows change, revealing more detail. And some of these big craters like Ptolemy, the surface is lava filled, and the sun hits it at such a low oblique angle that you can see subtle changes in elevation across the crater floor.
You wrote four craters: Cassini, Aristillus, Manilius, and Heraclitus.
Yeah, those are obscure craters, and so since the magazine represented those, I looked for them on a lunar map and posted in two pictures. Not that one there. This shows three of them at once. That's in the northern part of the moon. Cassini, which yes, and then Aristillus. I think there's certainly an I in there. Aristillus, right there, and then
Yeah, no U in it.
No U in it.
Yeah.
Okay, you can see my short-term memory is playing tricks on me here.
And then the last U. I'm sorry, there is a last U, but it should not have an I in front of it. So.
Okay.
So it's Aristillus.
Yeah.
It's Aristillus, yes.
Mhm.
And then Manilius, and that's there. The next one was much more difficult to find. It's in the Southern Highlands, which is all just a mass of craters. Can you switch to that one?
Let's see.
Ooh.
There. And there's Heraclitus, and that is right. No, not there. Nope, right there. I've got my cursor on it, but of course you can't see that. No, down to the left. Yeah.
What is that? What are we looking at?
Heraclitus.
Oh,
It's in the words in white over there.
oh, I see it. Yeah, right. Heraclitus. Who the heck was
That's
Heraclitus?
something you have to have a map and you have to look for. It doesn't stand out by itself like the craters up in the northern reaches do.
Huh. This is the same face we watch with all those big flat mares. I don't see any sea of Tranquility anywhere.
Well, this is very highly magnified, and it's in the southern region, which is just all craters. There's no seas in this area.
Uh-huh. Okay.
You can just in the dark side on this map, you can see Clavius over there on the lower left edge. It's got Aves, and it's between Porter and Rutherford. So that's the right there. That's the crater that the monolith was in 2001, A Space Odyssey. Very distinctive crater.
Yeah, I'll never forget the opening of that big round bulbous ship landing with all the stuff that was hitting from that blast filtering into the air. Remember that scene? Wouldn't look that way in real life at all.
All the dust.
Yeah, the dust flying up as it settled down into the moon base. So that's one that Kubrick didn't get to. You want to fade from this into the Vertex mission?
Jerry, I want to make a just quick note here that I saw this page where they have all sorts of moonshots, and its title of it says Gazetteer of Planetary Nomenclature, International Astronomical Union Working Group, and it's associated with NASA and USGS somehow. And you can search for just about anything, and they'll give you a little shot of where things are at. Like this was Heraclitus.
Yeah, Heraclitus. He was a Roman. He was a Roman historian. Wrote a lot.
You can zoom in or zoom out and move it around.
There's a lot of very good maps on the moon and Mars too, online. Matter of fact, Google does one of each. Google Moon and Google Mars.
And Cassini has been used twice, hasn't it, in the space programs? One around Saturn, and it's been a crater for many years. He was also obviously Italian.
Okay.
He worked in France.
He did?
Mm-hmm.
What was
Worked
his
in
first
France.
name? You know,
Don't forget about the Cassini division in Saturn's rings.
And there was not only him, but his son. They were both
Yeah.
astronomers.
Good job,
Right.
Chuck.
Cassini the elder and Cassini the younger. So anyway, Lunar Vertex mission. Scattered across the moon are strange light-colored swirls in the surface. They don't have any projected geometry. They're not hills or valleys or craters. They're just light colorations. And the they're not entirely sure what they're due to, but there's going to be a mission, a lunar vertex mission, that will look specifically at magnetic fields on the moon. And the consensus seems to be that these regions are regions where there's a local strong magnetic field in the moon. And that has caused, that basically put an umbrella over that part of the moon, so that solar radiation, the protons incident on the moon, have not weathered or aged or discolored the surface of the moon. So these would be protected areas. Yeah, might be of use for some future astronauts, but that's pure speculation. So the idea is very intriguing. Since the moon does not have a general magnetic field, how come it has a strong enough, if it does, how does it have a strong enough magnetic field in a few local locations?
Local chunks of iron that are magnetized.
Possibly.
Is that what's white? Iron?
No, the white is where it hasn't weathered.
Hasn't weathered.
Yeah, the proton bombardment hasn't changed the color.
Okay. Based on your notes, Jerry, you want to know what I wrote down? I kid you not. This is exactly what I was intending to say. Strange light-colored swirls scattered across the moon, and scientists cannot explain them. In parentheses, I said, but Jerry Wilson probably can.
No.
And that's exactly what you sent and what I said.
The only thing I know is what I read in the papers.
Okay, well, that didn't make it into your notes. They say we don't know what they are. Reiner gamma or Reiner gamma is a big one. White swirling paisley-like pattern that we're going to land on, apparently, with a Vertex mission in 2 years.
Yeah.
Being readied right now, I guess. What do we know about that mission? What are they going to learn or do?
We're going to map, among other things, map magnetic fields.
Okay. It's just northwest of the quadrant. What does that mean? A real mystery. No one knows how they got there. Reiner gamma. Gamma is a Greek letter. It's also the name of some nasty waves. So I suppose there's a reason that's on there, part of the name.
Well, it's the area of a crater called Reiner, and so they have alpha, beta, gamma, as sub features within that.
Oh, I got you. Any of you know what Prism stands for? That's the Prism class mission, the first of payloads and research investigations on the surface of the moon, PRISM. And it mentions some guy named Blewett, Blewett, and I looked back before his name showed up and couldn't find his whole name or any reference to him before, unless I missed it. You know who Blewett is?
That sounds like you blew it.
You blew it.
I edit these so that to shorten them so we can skim through them real quick. I may have left that piece of information out.
Yeah,
Sorry,
well,
Dr. Blewett.
he's the main investigator of the project, and sure enough, it makes me a straight man for Tom Whittemore.
These are easy. Give me something hard.
I guess this is an international effort, gentlemen, among what, France, Sweden, and Canada. Aerospace firm called Canada SYS with a multispectral microscope. What's a microscope doing on this thing? That was in your talking points. So I expect you to talk about them.
Where does it say microscope?
It says, I wrote it down right after Canada NSYS Systems, an aerospace company near Toronto, building the multispectral microscope. Maybe they misprinted it.
No, it's a microscope that's on a rover.
Oh yeah, the rover.
Yeah.
The rover part, right?
Yeah, the Lunar Vertex mission is going to land a rover in this area, and it's going to measure the surface, but it only has a 2-week mission, 14 days, because it'll land at dawn in this area, and then it'll have sunlight for 14 days, and then after that, it will not survive the lunar night.
Oh, no kidding! Wow.
Yeah.
You say sunrise? You mean first light of the moon, the first crescent, new moon?
No, the first light in the area where it's landed.
Which would be past first quarter.
Oh, I see. Got you, right. So we're looking at Reina Gamma, are we not? We were a while ago. Okay, is that the one they showed us? That
Yeah, you can see.
The two pictures are of Reina Gamma. One is as it looks from Earth, which is foreshortened, and the other one is corrected for what it looks like face on.
Uh-huh.
Yeah, and then Tom was putting up an image showing that it's at the waning crescent phase that it's prominent.
Big figure 8. Tim Crawford, you must have a question about this. You could post, on YouTube and we'd get it, or whoever else is.
Jim and Tim are chatting. They're in the chat. They haven't said anything yet.
Oh, well, read us their chats.
Oh, nothing special yet. Jim said that quasars and sea stars have been around for a long time, and Chuck kind of pointed that out, that Chrissy's been in it for a long time.
Mm-hmm.
A lander, and off the lander will go the rover. They don't have a name for the rover?
Well, Vertex.
Yeah. Chuck, I was going to ask you, because you know a lot of history of the museum. Wasn't there a Samantha who followed Chrissy as the director? Okay.
Now,
and
Samantha,
then,
Samantha was Javier's assistant. She went on to work at Lowell Observatory as a historian, and now she is in charge of astronomy at the National Air and Space Museum in Washington.
That's pretty neat.
Yeah.
That's a career that was really launched.
Yeah.
Yeah, so I think she, for a little while, was up at the Lowell Observatory in Flagstaff. Yeah,
as a historian, history of science.
Okay.
I have a question for Tom Whittemore. Tom, what does Vertex mean? I guess
a high point.
A high point. Okay.
Yeah.
Or where two things meet.
Two things come up and peak, if you like. Yeah.
You suppose that's the same word and they use in weather? Vortex?
No.
This is
vertex, like the vertex of a triangle. That's a point.
Oh,
Yeah,
vortex. Ron, a vortex is an eddy.
Yeah.
A swirly. To be real.
And vortex might be actually more appropriate for this Reiner Gamma area.
Yeah.
Well, there's all these new weather words or phrases that never came up as we were growing up. Polar vortex, what is it? Aeronautic river? No, atmospheric river, and other things. But anyway, that's a different subject. So Lunar Vertex, we're going to watch that blast off in 2 years if everything goes right.
Everything gets funded, stays funded, yes.
Any of you gentlemen, before we leave the subject, are going to aim your instruments at the moon this week?
Probably I will out back, just with a little tractor.
Okay.
Yeah, these are pretty phases, Ron. These are awfully pretty phases. You see a lot of contrasting features.
We'll probably definitely show it up there next Saturday.
Yeah. Yeah, it'll be quite bright.
The sky was pretty good last night.
Oh, it's excellent here.
Yeah.
What if
At the museum observation, it's going to be quite prominent, so we'll probably have a lot of people on it. And Pat will be on it with a camera, showing it on a monitor so that people can point at craters and ask what they are. And I'm going to have the little bracket so people can clamp on their cell phones and take pictures of it.
It's nice. And to champion Mercury one more time, if you're not sick of me, I did see Mercury in binoculars about 10 minutes until 6 Sunday morning. Okay. And it's really been fun for me watching it sort of like migrate from the southeast towards the left, towards where the sun is coming up. It's getting very, very, very low though. So if anybody would like to see it, get up before 6 and then use binoculars. You're not going to see it without binoculars. Okay.
Okay, is it in what they call perihelion? It takes 33 or so days, doesn't it, to get around the sun?
88.
88 from Mercury, yeah.
Oh, yeah. I'm thinking of its distance. Distance is about 30 something million.
But you will need binoculars, Ron, to see that. And of course, you will have to have a nice low horizon towards the southeast.
How do you study your binoculars, Tom? Do you have a clamp?
No, my hands. So I use birding binoculars. They're 8x42s, but they're really nice. They're made by Vixen Vipers, the Vipers. So they're birding binoculars, but they give you a good punch of the sky at night. Really nice. They're not heavy, Ron. They're not heavy. So I can easily use them, just with my hands.
Well, just real quickly, give a bird report. Have you spotted any weird, strange, rare species before we go to the next subject?
There's a
bird.
cat.
Birds? Nothing rare.
Okay.
I still hear the white-crowned sparrows out there. Actually, haven't left the area. I'm waiting for the hooded oriole to appear because our loquat tree is full of fresh fruit. And they usually show up for the loquats. They have a real sweet tooth. So.
Aha. Well, gentlemen, we can go out to M57 now and then end up with bigger, faster galaxies in the Milky Way. The ring nebula I just learned is M57, as Tom called up space. A few hours before sunrise, the moon is set, sky is darker, constellation Lyra, L-Y-R-A. It's 40 degrees high in the east, climbing with its bright star Vega blazing at magnitude 0. But just 7 degrees southeast of Vega, in between magnitude 3 stars Chelyabinsk and Sulafet. That's my law firm. Is
No, that's Dewey, Cheatham, and Howe. Vega. It's easy to spot because this trapezoidal figure of Lyra is an easy asterism to see up there.
Yeah.
But once I put my telescope where M57 should be, I sometimes have difficulty actually picking it out because it's so small that I pass over it thinking it's a star. So you have to have a fairly high magnification to notice that it's the nebula. And when you go to high magnification, your field of view becomes very small for searching.
Yeah.
It is detectable in binoculars if you know to look for a very small object.
Right. But not the central star, Chuck.
Not the central star, no.
I've seen my 18-inch, in a good dark sky, the central star.
Yeah, the central star is 14th magnitude.
Yeah,
So
I think we've seen it through the 24 at Westmont.
Oh, yeah, definitely.
Yeah,
well,
there it is.
forgive my ignorance again, but which constellation is Lyra? What is it depicting?
A harp.
It's a harp.
Oh, a harp. Lyra the harp. Okay. And there's the ring. We're looking dead on.
Yeah. Or some people, Ron, call it a lyre, L-Y-R-E. A lyre.
Okay, lyre, and there's a lute. That's another.
Just a little history here. M57 was one of the first things I ever saw as a little kid through a borrowed 6-inch telescope in the backyard in Indianapolis. My brother Paul showed that to me, and this is why I went into astronomy. One summer he borrowed it, it was probably about 1957, I would guess, roughly there. And so I was an 8-year-old kid, and he borrowed this 6-inch telescope that was homemade. For the counterweight, somebody used an agitator from a washing machine, but it was so good. We never saw the central star, but I grew up learning that Paul called it the smoke ring. He told me it was called smoke ring.
I've heard it called that.
Yeah,
you won't see the structure you see here in this photograph. You only see what's the brightest ring just before it turns blue going inside. That's what you'll see visually.
Yeah, at outreaches, we often call it the powdered donut in space. And, June 3rd is prime viewing time for it, and that's also National Donut Day. So
that's pretty good. Yeah, Vega comes up, by the way, around 12:30 in the morning. I said hello to it. I just happened to be up.
It doesn't stay below the horizon long because it's pretty far north.
That's right. That's right.
But you need a Hubble to get a picture like this, right?
Yeah, that's got a lot of structure on.
Yeah,
amazing structure.
Well,
either a Hubble or very long integration. Lots of time looking at it.
You guys see there's a galaxy? Yeah, I see that, Tom. Yeah.
What is that? Anybody know?
Yeah, I've seen it. I think I've seen it before, but only in pictures.
I
couldn't tell you, Tom. It's an NGC of some sort.
Oh, yeah. There's lots of galaxies in the background on this.
Yeah, you can see some little edge-on ones below there.
That's right. Those are very, very faint.
Yeah.
But we're looking at the puffed outer layers of a dying star. Here's
that's a white
dying sun-like star. It did not nova. It wasn't massive enough to create a nova.
Yeah, it fizzled.
Supernova, yeah.
So I think that they say the cloud diameter is like 1.5 light years across.
Is that right? Okay.
That's probably the smaller inner part.
Huh. Is there a white dwarf in there or a,
Yes. Yeah, that's the central star, Ron.
Yeah,
it's a white dwarf? We can see it?
yeah.
Yeah,
If you have a
I've
big
seen
enough
dot in
scope.
the middle.
Yeah, I've seen an
Okay.
18-inch. No.
And it wasn't a nova. It exploded, didn't it?
No.
Oh,
This
no,
is
no,
more
no.
like a burp than an explosion, Ron.
Right.
That's sloughed off. Interesting. Wow. Ringed nebula. Now, I wonder if we would be able to see that if it were edge on instead of full on. What would we see? Just a big line across the sky,
It
right?
would probably be hourglass shaped.
Uh-huh.
Okay, but we're looking at it end on.
And there's the blue in the middle, there's a white ring around that, and then there's red stuff out beyond. That's
Yeah,
all.
Well, this is kind of, artificial colors.
Yeah.
Ah, pulling a fast one on us. Ring nebula. All right, another nebula. It's not a planetary nebula, right?
Yes.
Yes,
Yes.
it is.
And even though there's no planets involved, what's the reason for that again? Why do they call it a planetary? It's a lot of dust.
When they were first discovering these things, they look greenish. They have fluorescing oxygen, and that gives off green light, and your eye is sensitive to green. So people saw greenish dots, okay? And the planets they were finding around that time, Uranus and Neptune, were greenish dots. So they called these things planetary nebulae, clouds that look like planets.
And that stuck.
Yes.
Yeah.
What are the other kinds of nebula that are not planetary?
Emission nebula. Well, this is emission nebula is a more generic term. These are also emission nebulae.
Yeah. Reflection.
Reflection nebulae.
Those will look more blue because they normally are around hot, bright blue stars. So you get reflection.
Okay. And so it's always the remnant of a star, any nebula, right? It's
Yeah,
Well, no.
it could be a big field of gas.
Yes. It just
Aha.
means cloud.
Just a cloud, regardless of how it was created.
Yes.
Well, somebody
And
said,
galaxies used to be called spiral nebulae because they didn't know what they were at first.
aha. Well, I get these strange emails from somebody in the club, and I wonder what a Hosta nebula is.
That's
Sounds Hispanic.
That
Never-
means until it's cloudy.
Pretty
Ready?
good.
The old ring, the smoke ring. You ever seen a guy back in the smoking days who could blow those rings?
Yeah. Oh,
Yeah.
yeah.
I don't think my dad ever mastered it, but it's what put him in his grave. Can we go to the next subject, or you want to talk more about the ring? 2,300 light years away, so it's probably not going to bother us.
You'll see different numbers for the distances ranging from about 1,300 to 5,000 for things like this, just because they're not uniform, and so it's often hard to figure out what the distance is.
Okay, now that leads to the next subject, gentlemen, and a question that I had when I looked at Andromeda being blown up and at a tilt. It's sideways. We're sort of looking at it at an angle, right?
Yeah.
That means
Yeah,
the stars that are closest to us on this side, nearest us, left what, 2 or 3 million light years, or is it billion ago? How far away is Andromeda?
It's roughly 2.5 million light years away, but one
Right.
side is a couple of 100,000 light years closer than the other.
Okay, so why wouldn't that warp the galaxy, since the far side is even older and therefore they would be not in exactly, I guess it doesn't matter, does it,
No,
for those kind of numbers?
Andromeda is actually warped. If you look at the pictures, the outer rim has a different plane than the inner core area.
And that's natural.
It's the result of a collision that happened a long time ago. Our galaxy apparently has a similar dent in it.
Okay, well, this
Like a potato chip.
Yeah,
our galaxy got a little bigger, didn't it? It's not 100,000 light years across anymore. It's over that
200,000.
200,000, and Andromeda is about 1 million.
No.
no, we're about the same size.
Yeah.
Oh, we're about.
They just have a lot more stars.
Well, this is not Andromeda we're looking at, though.
Now, what we're looking at here is UGC 12591,
There you
Which is
go.
the third most massive known spiral galaxy. It's bigger than our galaxy, the Milky Way, and it's rotating, has a mass estimated at 4 times the Milky Way's mass, and it's rotating much faster than our galaxy is. 500 kilometers per second,
How in the world?
which is almost twice that of our galaxy.
At
So
some distance.
Jerry,
that?
would that be that the galaxy is like pulling its arms in like a skater spins faster and gravity's pulling things in so it spins faster? What do you think?
Yeah.
Galaxies don't act like that because of all the dark matter.
Right.
They tend to rotate, all the stuff at every distance tends to rotate at the same speed.
So
Like a
that's
solid disk.
it's more likely a result of collisions that happened along the axis and transferred a lot of angular momentum.
Yeah.
You know, along the plane of the galaxy.
Well, now
So
this is,
think of it like this. If you have 2 counter-rotating tornadoes and they hit each other, they basically cancel each other out and stop. But if they're rotating the same way, then when they hit, they add the angular momentum, as Chuck said, and you get a super tornado.
wow. But now this is the third largest rotating or spiral galaxy, because there are bigger galaxies. What's the ones that started with the word L last?
Elliptical.
Oh, elliptic. Yeah, that big fuzzball. That's just huge and would gobble up these things like peanuts that aren't radial. They're not turning. Just the big fuzzballs, the big cotton balls in space. Elliptical, right? Those are the biggest of all, but the third biggest spiral galaxy, right behind, let's see, ISO HDES 27 and J2345-0449.
Yeah, you remember those.
Yeah, I remember
Yeah.
those.
Kind of rolls off the tongue, Jerry. I
Yeah.
was going to say,
And
so how far away is this thing? There's amazing detail in the dark lanes.
Yeah.
It's amazing. Do you know how far away, Jerry?
Might be here.
I don't.
It says 400 million years ago,
okay.
the light we see today. So
Oh,
400
yeah.
million light years.
That
400.
gives you the distance then.
Boy, there's a lot of faint galaxies in the background too, including a barred spiral up there on the left. Incredible detail, huh?
Yeah.
It's in Pegasus, so there's a cluster up in there, Pegasus cluster of galaxies.
Yeah.
Mm-hmm.
And the
It's
fact
not
that it's
that far.
UGC is Uppsala Galactic Catalog, so that means it's probably pretty faint, I think. Most of those
Yeah.
are.
Yeah, it's 14.5 magnitude
Okay.
Gettable.
integrated light.
How
And
do you-
it's apparently, oh no, that's in general. Mhm.
How do you suppose, gentlemen, they learned that it's going 500 kilometers an hour, which is about 400 miles per hour? You can't see anything move. How do they know?
Spectroscopy.
Yeah,
Right. Get the Doppler shift on it from one edge to the other.
So miles per hour or miles per second?
Per second. Yeah.
It's kilometers per second.
Oh, yes, you're right.
whichever side is rotating toward us is blue shifted, and the other side, the other wing is red shifted. The one
So
moving away from us.
you suppose since it's not split apart, it's got a lot more dark matter than maybe we have?
Well, it's got more regular matter, so it probably has a heck of a lot more dark matter.
Yeah.
And so
There are- I've read that there are galaxies that are basically dark matter with a few stars. And then there's galaxies that are all bright matter with almost no dark matter.
Mhm.
how
So I think we have a ways to go on figuring all this out.
Sure.
I remember, Mr. President, at one point years ago, when we used to meet together, you actually voiced doubt about dark matter. You were unsure about it, and a lot of people still are. Some people say it doesn't exist.
So, yeah, I don't remember stating it that strongly. I said I wouldn't be surprised if the simple explanation of having dark matter is overturned, and there's some other way to account for the odd performance of gravity in these systems.
Yeah.
Well,
Dark matter just seems inelegant.
but their science is plunging ahead, trying to find a muon in one of those collider tunnels. Like you can see one of those suckers, you know?
Muons are fairly common, I think.
Yeah.
Yeah. Yeah.
I'm not following what you're asking.
Okay. Oh, well, muons, isn't that the
Muon.
Yeah, M-U-O-N?
Yeah,
Yeah,
muon.
yeah, those are well-known and well-studied subatomic particles.
Okay, gotcha. All
You're
right.
thinking
One,
axions, I think, Ron.
I'm thinking of what?
Axions?
I thought a muon was the basic invisible part of dark matter. I thought that's what
No.
they
So you might be thinking of WIMPs,
WISP. I was. That's exactly
which is a proposed solution to dark matter, but it has not panned out yet.
That's right. Geez, amazing. Faster galaxies, come on. But you know, they show those computer generated collisions and the suckers that go through each other and swirl around. How long does that all take before it steadies itself out and looks like what we just saw on the screen?
Couple of billion years.
Several billion years.
When two diffuse gravitational systems collide like that, it's like fluids. It's like two smoke rings colliding in the air. You know, they pass through each other and then they oscillate back and forth. There's no actual collisions or collisions between actual mass.
The stars.
Except for maybe large gas clouds.
But that's happened to our Milky Way several times with some of the neighborhood group, the local group, right? We've swallowed them up.
Yeah, smaller galaxies.
Yeah. So we're not going through that. Shall we talk about the sun for the next quarter hour
Sure.
or less? You didn't send a lot of words, but there's some great diagrams and photos and pictures here. They got the boiler room, the fusion factories, hydrogen to helium and all the way up.
Tom, can you show the picture that I sent?
Today?
Yeah, today. It is very similar to the one that you have up there, or that I see on my chart, the sun. But I think it's slightly better.
Not that one.
I like the first one you said better, but oh well.
Okay, let's go to the first one.
Okay.
Do the first one.
I've got a couple different screens here. I'm trying to figure out which one I'm looking at here. Number 12. Okay.
So I'm the only one that confuses myself with my computer.
There's so many screens I have.
Yeah. So this is a representative of our sun. And the core, you see here, super white, is above 10 million degrees, which is enough heat. And that heat is generated primarily by gravitational crushing of the mass above it.
And that's Kelvin. That's Kelvin.
Yeah.
Kelvin, yeah. And so, well, you could only be off by 372 degrees. So,
well, more than that for Fahrenheit.
Yeah, that's true.
Why don't they give it to us in Fahrenheit?
I heard it.
Nobody uses Fahrenheit.
Oh, anyway, so the core is now fusing, and it's fusing hydrogen. The sun is basically made out of hydrogen. There are other things there too, but it's primarily hydrogen, and it's hydrogen that's fusing to helium, and that will go on until the hydrogen is pretty much all used up, and then the core will collapse again, and you'll achieve a higher temperature inside due to gravity, and then we will start burning helium. Now,
Tom, you shouldn't have gone to this one yet. This is a very large star, so that has nothing to do with the sun. There we go.
Yeah, so thank you. So this shows the layers of what's happening, because we talked about this very briefly last week, but we didn't have a good picture. So these are the regions of the sun as it is now, which is burning hydrogen. The source of the energy is the hydrogen fusion. That works its way out through all this structure of helium and other elements. And that radiation coming out is what counters the gravitational pull, causing it to collapse. When that radiation stops in the middle, then gravity will not have anything to keep pushing against it, and the gravity will win, and the thing will contract a little bit, and that'll cause the core to rise up to where helium fusion can start, and then it will reach a new equilibrium and it will sit there. So right now we have the core, then we have a radiated zone where stuff comes out, photons created in there are radiated out, and they're radiated and absorbed and re-radiated a lot. So I think one of these, either to the total surface or just to get to the top of the radiated zone, it takes about 100,000 years for a photon to make that trip. Now, once we get up to the convective zone and we pass the barrier between the radiated zone and the convective zone, which is the tachycline, this is the region where you're starting to get material transport of the heat. And so the radiation is still coming up, but it heats up material, and the material will flow up to the surface like in a pan of boiling oil. If you look at that on the stove, you see little convection cells coming up. And when they reach the surface of the sun, the convection cells, you can see them. Chuck, do you have anything you want to say on this?
No, I was having a cat problem.
Oh.
The only thing I'd just add, Jerry, is that, the photons created in the core, are gamma ray photons, highly energetic. And by the time they, like you said, hundreds of thousands of years, they random walk, you don't get the same photon out on the surface of the sun, but something that appears more green or yellow, okay? Because the temperature on the surface of the sun, the chromosphere, we call it, photosphere. Photosphere is about 5,800 kelvins. Okay, but so anyway, it's you think of this thing as a photon being generated in the middle of the sun, a very, very, very energetic photon, and it random walks and it gives up energy, and it gets more, and then it gives up and it gives up. By the time it gets to the surface, okay, it's a photon that's only about 5,800 kelvins. Okay, so it appears yellow or green.
And it's not just one photon, but probably numerous less energetic photons.
Yeah, you're right, Chuck. It's an ensemble of photons. Yeah.
God, it's a madhouse.
Now, when
you can see how it's semi-transparent there, and then there's the chromosphere, which we look right through. Yes. And that's basically just fluorescing hydrogen.
Well, now our sun is made up of a former star's material that it manufactured a lot of, right?
Yeah, that's where the extra elements beyond hydrogen comes from.
But that's very little. That's just like a little scum of contamination.
Right. If you buy a telescope to look at the sun, because the hydrogen, it's mostly hydrogen. Hydrogen is where the action is. So you would get a telescope tuned to hydrogen, but you can get telescopes tuned to other elements like chromium. And there the sun is green, but it's much, much fainter if you look through it, because there's not much chromium on there, but you're looking at that one spectral line. I forgot what I was going to say, so please.
So Jerry, you have a calcium filter on one of your solar scopes, right?
Right. I was just going to mention calcium.
Yeah, that's calcium. Kind of a bluish look.
Yes, yes. Mm-hmm.
So when you have this, all these elements, hydrogen, calcium, in there, of course, because it's so hot, they're all ionized. So all this stuff is matter. It's electrons and protons and neutrons. The neutrons, of course, aren't charged, but the particles are subatomic particles are all charged. So as they move, then you get magnetic fields, and they're moving very fast, so you get intense magnetic fields. And so this moves, the field that studies how this kind of plasma moves is called Magneto Hydrodynamics. And it's kind of a headache mathematically, but it has interesting effects. But what happens is that also these different portions of the sun rotate at different rates. So the magnetic field lines that are created, they get twisted up, and they get twisted up. And as they get twisted up, they some of them bump out of the surface or twist out of the surface until enough energy is built up that they snap and reorient themselves, reconnect. And then you get flares. And what you see here is basically sunspots and flares. And these are following magnetic field lines that are coming up out of the sun. As a field line comes up out of the sun, the field line rises in the atmosphere, and it takes the randomness of the hot atmosphere and it aligns them along the magnetic field, which makes the atmosphere slightly cooler. And so it condenses. And then as it condenses, it falls back toward the surface. So the material in one of these loops is actually moving toward the sun's surface, but the loop itself is moving up away from the sun.
And a common misconception is that these loops are called flares, but the flares are just like the bright regions where energy is being released, and these loops are called prominences.
Excuse me, I used the word wrong. Yes, you're right.
Huh. Well, these magnetic fields out of the sun indicate there's a lot of metal. It certainly doesn't have iron in there much, or it would collapsed, right?
No, there's iron, but it's in gaseous state, and there's very little of it.
Yeah.
And
And
it's moving charged particles. It doesn't have to be metallic.
right.
Okay, fascinating stuff. But now the very fact that we're sitting on a planet that came from the same dust and gas that made the solar system at the beginning makes us, what, second generation, third generation? How many stars blew up to make the stuff that makes us? Because we got all the elements here on Earth.
Well, at least second generation.
Now, this will be confusing, but before they knew about these generations of things and how stars were made out of old stars, they called the stars that are out there now population 1. And the earlier stars that were mostly hydrogen, they called population 2. So population 2 came before population 1, now that we know.
Right.
And there's even a population 3, which is really, really old stars.
Right.
So science has a lot of these things because science adds mechanisms to knowledge that's empirical at first. And another example of this is electric current. When people didn't know what it was that was moving, they just arbitrarily picked the motion of positive charge as the direction of current. Electrons actually do the moving, so the electrons move opposite to the current.
Thank Benjamin Franklin for that.
Yeah.
Right.
And another thing about the sun is those dark regions that you see on the sun they're called sunspots. That's where you have these immense twisted magnetic fields, and they actually block the transport of energy up from below. And so it's a cooler region below them, and that's why it looks dark.
Mm-hmm.
Right. Yeah, those regions are they're not really cool, but they're cooler. They're typically 4,500 kelvins, and the rest of the sun is more like 5,800.
Yeah.
If you had a sunspot all by itself, it would be brighter than the full moon in the sky.
Yeah. Let's go back to the sun, Tom. Okay, now let's go to the layered fusion topic. Not that one, the one that shows all the layers inside. Not that one.
This one.
There. Yeah. Yeah. So in this star, the star has a layer out here where hydrogen is fusing.
Well,
then it has a layer inside where helium is fusing. So this is a much more massive star than our sun. Right. And it will go through, it's showing all the different layers that it's going to go through or is going through. Carbon fusion. Now there's a lot of elements in the periodic table that are missing from this, up to iron. Iron is just collected as an ash in the core. It does not generate heat when it fuses, so that it's not going to go through any fusion to produce anything higher than iron on the periodic table until it blows up. And then you get a super crush of energy, which produces in a flash a lot of elements above iron. But the ones that are missing below iron are because, for example, lithium, you would think that you first fuse hydrogen to get helium, helium to get lithium, but you don't see that here. You fuse, you get carbon fusion, and then the carbon decays back to produce lithium and the other lighter elements that are skipped over by direct fusion. And that's hinted at by the table that's next.
Decays meaning it loses protons and electrons?
Yes, because some of these things that are made are isotopes and they're unstable. For example, here you get 4 hydrogens. In hydrogen fusion, you take 4 hydrogens and you get 4 heliums plus 2 electrons plus 2 neutrinos plus some energy. Now,
Jerry, that's not 4 heliums, it's helium
oh,
4.
yes, you're right. Helium-4. Thank you.
Or hydrogens.
Which means helium-4 would be two protons and 2 neutrons, right?
Yes,
Yes.
yes, that's correct. That's the regular
Two
neutral. That's neutral helium and is stable. And this one, you take 3 helium-4s and you get a 12 mass carbon plus energy. Now, 12 mass carbon plus another 12 mass carbon gives 24 magnesium plus energy. A 12 carbon plus 4 helium gives oxygen 16. And so there's a lot, as you get up through this chart, there's a lot of extra crap floating around. Here there's 2 electrons. You also get neutrons floating around, and they can combine with atoms. I don't see any like here like that, but oh, there's one down at the bottom. Iron 56 plus a neutron gives iron 57. But it becomes a very complicated table. These are the main ones that you get. But
right. This is simplified. There's other things going on, like the carbon can act as sort of a catalyst for the hydrogen and helium reactions that earlier occur. And so there's other stuff that goes on, but these are the major steps.
yeah.
Oh,
You know, Jerry, what I thought was kind of interesting is that on these supermassive stars, that how long it takes to burn out on these heavy stars. And I have this one chart here that kind of gives an idea. I don't know how accurate it is, but let me see if I can show it to you. It shows that hydrogen burning for a massive star is only 7 million years. And then the helium only goes for 500,000 years. Carbon stage is 600 years, neon's 1 year, oxygen 6 months, and silicon is 1 day. Before and then you get iron, silicon's going into iron, and then it blows up in just within a day, I guess.
Yeah, that's 1 day before the supernova explosion. So, but that's a 25 solar mass star. And you see the thing in parentheses up there, heavier stars burn their fuel faster. It's going to take 5 billion years or close to it to burn the hydrogen in our sun.
5 billion.
Yeah, go ahead.
and we continue this conversation next week and get into more depth. I got a lot of questions. We're over time, gentlemen.
Okay.
But
Well, that's okay, but I think we've covered the basics of it.
yes, we have. Fantastic. Well, look, you guys take care of yourself in this cold. Tom Whittemore, keep looking at the birds and the stars with the binocs.
Yeah.
And what's going on real quick with the Oregon Society, Bruce? You guys alive yet?
Nothing. I mean, we've been shut down for 2 years.
All right, got rid of your mask. Chuck, next Saturday, we'll see you at the meeting, what, at 4:30 in sunlight, and then we'll stick around and load our instruments for the big star party Saturday night, followed what, 1 week or 2 weeks later by Westmont, the third
6
Friday.
days later.
And Tom Totten, take care of yourself and Suzanne, and say hi to Pat, and the dog needs petting, Mr. President. We'll see you all next
And
Monday.
the dog's sleeping on my green screen.
All right, this is great. This is the SBAU Astro Hour live on YouTube and from Zoom. We'll see you in the future in a week. Number 54
Yes.
coming up. Thank you.
Bye-bye.
Bye-bye.
Bye
everybody.
now.